So today's topic is consanguinity. It's one of the common term that you encounter when you deal with a genetic disorder. People always ask for consanguinity in the relationship of the parents. So what is consanguinity? Consanguinity means union between two individuals who are as close or closer than second cousins. So what all relations will come under consanguinity? Second cousin marriage, first cousin marriage, uncle, niece or aunt nephew marriage, first degree consanguinity, which is not present in India, like son, mother, siblings marriage. So all these close relationship marriages or relations will come under consanguinity. Why it is important? Whenever you say consanguinity, it literally means you are talking about the risk of an autosomal recessive disorder. Because in autosomal recessive disorder, two mutated allele has to be present for the disorder to occur. Since the relationship is within close blood relation, there is a higher chance that two mutated allele will come together in the offspring. That's why consanguinity is important. So consanguinity means higher risk of autosomal recessive disorder, not autosomal dominant, not X-linked dominant, not X-linked recessive, only autosomal recessive. Why it is important? It increases the chance of autosomal recessive disorder, which are extremely rare otherwise. Before going into types of consanguinity, I will introduce another term that is called inbreeding. So what is inbreeding? So when we calculate frequencies and of very rare alleles, etc., we always consider the term random mating. So we know that there is something called Hardy-Weinberg equilibrium in population genetics, which using which we calculate the frequency of carriers, affected individuals, unaffected individuals in the population. So in that, one assumption that is made is that the mating is random. However, in real life scenario, mating is not random. People usually find their partners from their own community. There will be some geographically isolated areas like mountains, some islands, some coastal areas where people marry within that the close community. So mating is not random. So what will happen? So there is higher chance that people will find partners from that own community. So that is called inbreeding. And why it is important? Because there is inbreeding, there are high chance of having consanguineous relationships and higher chance of rare disorders in that community. And to express inbreeding, there is a term used which is called inbreeding coefficient. The definition is probability that a homozygote has received both allele at a locus from the same ancestor. So I will explain that with an example so that you will easily understand the concept. It is denoted by the term F. And we explain consanguinity if the F is more than 0.0156, that is second cousins. I will explain all these values, how it is derived, etc. So let me explain what is inbreeding coefficient with this pedigree. So these are the grandchildren, parents, and this is a male. This is his sibling, another male. These are the grandparents. So the grandfather is a carrier for an autosomal recessive disorder. So his wild type allele, that normal allele, is denoted as A, capital A, and the mutated allele is denoted as small a. So what will happen? There is a possibility that he will give his recessive allele to both of his children, right? There's a possibility. Assume that he gave his recessive allele to both of his children. Then there is a possibility that this A will be transferred to their offsprings, right? So now these two individuals, this boy and this girl, they are first cousins. What if they marry? It is called third degree consanguinity. I will explain the concept of consanguinity and various degrees of consanguinity as we move on. So if they marry, there is a possibility that they will transfer this two recessive alleles to their child who will be affected. So how does this child got the recessive alleles? So that is derived from his grandparents, not grandparents, great grandparent. So what is the possibility that he will get a homozygous state and both alleles were derived from a common ancestor? That is called inbreeding coefficient. So it is obvious that if the common ancestor is very far away from his generation, the chances will be less, right? If the common ancestor is very close to him and in between there are only very few generations, the chance will be more. So this is called inbreeding coefficient. It does not just apply for recessive alleles. Look at this. In this, we see that this allele, wild type allele, got transferred to both of his children, then to next generation, and eventually this girl got both the wild type allele. Even she is a homozygote, and both of his alleles were derived from the common ancestor. Even this will satisfy the inbreeding coefficient definition. So inbreeding coefficient means there is a homozygote, and what is the probability that both of his alleles were transferred from a common ancestor? This is called inbreeding coefficient. And inbreeding coefficient has an equation. It is F is equal to half multiplied by proportion of genetic material shared between parents. So in this case, inbreeding coefficient means half into the proportion of genetic material shared between parents, his parents. So what is the amount of genetic material that is same for both of her parents, and that multiplied by half, that is called inbreeding coefficient. I will explain in detail when I explain pedigree. If F is equal to 0, that means there is no common ancestors in the recent pedigree, so there is no consanguinity. And F, the value of F is proportional to consanguinity, and the value of F is proportional to risk of autosomal recessive disorders. Now let's move on to first degree consanguinity. It's rare in India, for that matter it's rare in world also. It means there is a relation between father and daughter, mother and son, or siblings. Why it is important? Because how much genetic material will be common between a mother and son? It will be half, right? Father and daughter, it will be half, right? What is the genetic material that is common for the siblings? It will be half. So the proportion of genes in common will be half. And I already told you that F is equal to half multiplied by proportion of genes in common. So half multiplied by half, that is 1/4. So F will be 1/4, that is 0.25. And why it is important? F is proportional to the risk of autosomal recessive disorder. So F is half means a very high value, and there is high risk of autosomal recessive disorders in the offsprings. Coming to second degree. Second degree means proportion of genes in common will be 1/4. Here it was half, here it is 1/4. So what are the possibilities? A relation between half siblings, that means both the partners have one common parent, or an uncle, niece, or aunt nephew relation, or double first cousins. Double first cousins mean their mothers as well as fathers are siblings. In these three conditions, the proportion of genes in common is 1/4, and obviously if you multiply it with 1/2, F, you will get F. F will be 1/8. This is called second degree consanguineous marriage. Again, it is not very common in India, although it's still present. Let's move on to third degree. This is the most common consanguinity that we encounter in our population. This is the classical pedigree. That means first cousin marriage. So they have a common grandparent. And other possibility is the relation between half uncle and niece, or half aunt and nephew. So here if you see this lady, her mother and mother, for that matter even father also, and her partner are half siblings. So this combination is also known as third degree consanguineous marriage. So in this, proportion of gene in common is 1/8. So as we go from one pedigree to another, the proportion of genes in common decreases by half. So in first degree it was 1/2, second degree it was 1/4, third degree is 1/8. So F will be, that is inbreeding coefficient will be half of 1/8, that is 1/16. Coming to fourth degree, again the common ancestor is moving further. This is half first cousins or first cousin once removed. That is, previously the relation was between these two individuals. That means first cousins. However, in this pedigree, that is fourth degree pedigree, this is first cousin once removed. That is, one person has gone one step further away from the common ancestor. So what happens? Proportion of genes in common will be 1/16 and F will be 1/32. What will happen then? The consanguinity is decreasing, because of which the autosomal recessive disorders risk will further decrease. Coming to the last degree of pedigree, that is fifth degree. These are the second cousins. So the common ancestor is one step further away. So the proportion of genes in common is 1/32 and F is 1/64. If you divide 1 divided by 64, what will you get? You will get this value, 0.0156. So what is significance of this value? So when the inbreeding coefficient is 0.0156, or in other words, the proportion of genes in common is 1/32, it's called fifth degree. Another thing is that further away from this inbreeding coefficient or proportion of genes in common, the risk of autosomal recessive disorders is same as general population. So that means a sixth degree pedigree, we can make it. However, why are we defining consanguinity? Because we want to ascertain the risk of autosomal recessive disorders. What if the risk of autosomal recessive disorder in sixth degree pedigree is same as general population? Then there is no purpose of defining it, right? So after fifth degree, the risk is same as the general population. So we don't define sixth degree pedigree. The pedigree ranges from first degree to fifth degree. And people would like to know how consanguinity causes rare disease. So rare disease can happen in a non-consanguineous marriage also if both parents are carriers for a same disease. There is a 25% risk of the occurrence of rare disease in the offspring. However, let's explain mathematically how consanguinity causes increased risk of rare diseases. So consider an autosomal recessive disorder, for example, phenylketonuria, cystic fibrosis, say any other enzyme deficiency, methylmalonic acidemia, for that matter. Suppose the normal allele is capital A and the pathogenic allele is small a. The frequency of capital A, that is the wild type allele, that is the normal allele, is P. Frequency of pathogenic allele is Q. So since P and Q are fractions, obviously P plus Q should be 1. So if what is the probability of a person having a genotype of capital A, capital A? So it will be P square, right? Because the proportion of capital A will be P. So what is the probability that both the alleles will be capital A? So P into P, that is P square. In similarly, the probability of small a will be Q square, right? So what is the probability of A and small a? So there are two possibilities. One is first allele is P, second allele is Q. There is another possibility. First allele is Q, second allele is P. So if we add together, it will be 2PQ. So I think you understood the concept. And let's do one calculation. So in most of the autosomal recessive disorders, the recessive allele frequency will be very low. It's common sense, because if the recessive allele frequency is very high, obviously we see these rare disorders very common in your community. However, rare diseases are rare, so the frequency of pathogenic alleles will be very low. For example, for example, in some random disorder, for example, this is phenylketonuria. I'm taking phenylketonuria just for the example sake. If the recessive allele frequency is 1 by 100, Q square will be 1 in 10,000. That is 1 in 100 into 1 in 100. So that will be the frequency of rare disease. However, if consanguinity is present, for the example sake, I am assuming that there is third degree consanguinity, the most common consanguinity that we often see in our OPD. Then we have to give a correction factor for the equation. So the probability of autosomal recessive configuration will be Q square, that is there in the equation, plus Q into inbreeding coefficient. So this additional factor will come into play if there is consanguinity. If there is no consanguinity, what will happen? This F will be 0. So Q into F will be 0. So there is no need for adding this factor. However, if there is significant consanguinity, the F value will be significant. So there is a need for adding this correction factor. Then let's recalculate this equation. So the Q square will be, we have already calculated 1 in 10,000. So 1 in 10,000 plus Q is 1 in 100. F is, so it's a third degree consanguinity. So F will be 1 by 16. So the net value will be 1 by 10,000 plus 1 in 1,500. So if we ignore this value 1 in 10,000, it will be approximately 1 in 1,600. So the incidence shot up from 1 in 10,000 to 1 in 1,600, roughly an 8 times increase. So that's the impact of consanguinity. So if consanguinity is present, the risk of very rare disorders, it increases by multiple folds. That's the importance of taking a proper history, asking if there is any common ancestor degree, so that we can understand the degree of consanguinity and counsel appropriately. So in consanguinity, always think about autosomal recessive disorder. So consanguinity, the concept of consanguinity is for autosomal recessive disorders. If there is any doubt, please leave it in the comment box. I will answer. Thank you.